Hello and welcome to lecture number 6 in the course Advanced Robotics. Today we'll be continuing with our discussion of the Puma robot. We'll see how to assign the axis to the various joints of the Puma robot, then make the DH parameter table, and then proceed to make the various transformation matrices that will relate the end effector position and orientation with respect to the base frame. Okay. After that, we'll move on to forward kinematics and see that when you're given the link parameters and the joint angles, how we can get the position and orientation of the end effector with respect to the base frame. Okay, so we are continuing with our discussion of the Puma robot, and just to very quickly revise what we are doing when we are given a robot manipulator is that, for example, when we are given a robot manipulator having 3 degrees of freedom like this, the first thing that we do is we assign our z-axis and then the x-axis. So I assign my z-axis. So this is going to be my z0, z1. This is my z2, z3 axis. Then assign my x-axis. In this particular case, it is x0, x1, x2, and x3. Please look at the rules which I discussed a couple of classes back. Then we make the DH parameter table. In this particular case, I make a, alpha, d, and theta. We make the DH table and assign the various link parameters, the link length, the link twist, the offset, and the joint angle. So in this particular case, it is 0, 0, 0 theta 1, L1 0, 0 theta 2, and it is L2 0, 0 theta 3. Okay, this is my link length L1 and L2. Then what we do is we take each of the rows and put it into the generalized matrix. So this is my generalized matrix which relates the next frame to that of the previous frame. So I take the first one, then I get my matrix 0 to 1, then I take the second one, put it in here, I get 1 to 2, and I take the third one, put it in here, I get 2 to 3. Then I multiply all of them out and I get my final matrix, which is 0 to 3 in this case. Okay. Now, we also saw the example of, we started off with the example of the Puma robot. So I'll very quickly go through the Puma robot example again. And we did not complete in the last class, so we'll complete it in this class. So the first thing that we do is to assign our axis. Now, how do we assign our axis? The first axis is so this is a 6 degree of freedom manipulator. So the first thing that we do is to assign the first axis, which is the waist axis. And this is my Z0 and my Z1. So this is Z0 and Z1 there. That's my first axis. The second axis is assigned here, which is my Z2. Okay, so this is my Z2 axis. Then the third axis is assigned here, which is my Z3 axis. So that's my Z3 axis. Okay. Then at the wrist, we say this is my roll axis, which is my Z4. And then we look at the wrist part in more detail, and we see that this is my Z4. Z5 is in that direction, Z5. And Z6 is back here in this direction. In the last class, also I explained why Z4 and Z5 are in the same direction, because Z6 is actually that side. But if you do it this way, the 3 axes Z4, Z5, Z6 are orthogonal, but you'll not be able to assign your X6 axis, okay, because there is a problem in the DH parameter notations. Okay, so to avoid that, what we do, we rotate this and make it in this direction. So Z4 and Z6 are along the same direction. Okay, please refer to the previous class notes, which explains why it is done that way. Okay, so this is my Z3, Z4, Z5, and Z6 are along that direction. Okay. The next thing that we do is, this is also called the roll, pitch, yaw kind of wrist. Okay. The next thing that we do is we assign our x-axis. Now, please note that Z0, Z1 are in the same direction. Z2 is the one which is orthogonal to Z1. So Z2 and Z1 axis are intersecting at a point, and they are having 90 degrees between them. So this means that for an intersecting z-axis, the x-axis has to be out of plane, out of the plane containing the z's. So this is my x2. If this is my x2, I can also say this is my x1 and x0. So this can be my x0, x1, and x2 in that direction. x3 is in this direction. That's my x3. Okay, and my x4 is in this direction. Okay, so if I go back, go here, then x3 is this side. Now, please note that Z3 and Z4 are orthogonal to each other. Okay, their directions are orthogonal to each other. So my x4 is going to be perpendicular to this. So my x4 will come there. And similarly, x5, Z5 is here. So I put x5 and x6 here. Okay. So the problem I was talking about is if your Z6 is here, if Z6 is there, then what happens is, because Z5 is orthogonal to z6, z6 and z5 are orthogonal, then you cannot assign your x5 such that you can rotate z5 to make it z6. Okay, so that is what is the problem. So to avoid that, we put z6 down, and now x4, x5 and x6 are here. Okay, so now look at the distances between the various origins of the frames. So your origin of frame, please note this very carefully. Okay, this is something to note. This is the origin of frame 0, 1 and 2. I could have taken the origin of frame 2 here also. That I could have done. Okay, but just for simplicity, I'm making it here. So that's my z2 axis. This is my z2 axis. Okay, now the origins of 0, 1 and 2 are the same point. Origin of 3 is here, so that's frame 3. 4, 5, 6 is here. 4, 5 and 6 are there. Okay, now y-axis are not required, so we need not draw the y-axis. Now look at the distances. We are going to write our DH parameter table. So let's call it alpha A, D and theta. Okay, so this is my DH parameter table which I'm writing. There are 6 axes, so there will be 1, 2, 3, 4, 5 and 6. Now let's look at the first 0 and 1. The z's are the same axis, the origins are the same. So what will happen is this will be 0, 0, 0, theta 1. That is very simple because it's the same axis, right? So this is my same axis, so it will be 0, 0, 0 and that is theta 1. Okay. That means if when axis 1 rotates, what happens? The angle between x0 and x1 will change. So it will come this side or it will come that side, okay, on that plane. Okay. Now the second one, let's look at the second axis. Now the origins of the second axis is the same, but there is a 90-degree angle there. So there is a rotation of clockwise 90 degrees about the x-axis. So z1 rotates 90 degrees and becomes z2 clockwise. So this is a minus 90. Clockwise is taken as minus 90. This is 0, 0 and it is theta 2. Okay, origins are same, so A and D are 0. Now let's take the third one. Please note that the third axis is here. Okay, now the third axis, or the origin of the third axis, which is there. Now the origin of the second axis, you can imagine this as travel like this on that plane. So there is a distance of d3 there, plus there is, then it goes forward like this, and then it becomes that axis, right? Let me draw it with some of the color. Okay, so how is third axis going there? If you look at the third axis, it has traveled in this direction to that plane, and then along the plane it has gone there. So there is a distance d3 and there is a distance here, which is my a2. Okay, so what is the angle between the z2 and z3? There is no angle, so it is, they are parallel, so it is 0. Now what is the distance between the z-axis? It is an a2. And then what is the distance between the x-axis? There is a distance of d3, and this is my theta 3. Okay, now let's go to the fourth one. Now fourth axis, the third axis. Now let's go to the close-up view. So this is my third axis. 4, 5, 6 are here. 4, 5 and 6 are there. So the third axis has moved up and then traveled like this. So it has moved up by a3, so that's my a3, and traveled by d4. Okay, so it is moving up by a3 and then going on the right by distance d4. Okay, so now if you look at the DH table, what will happen is your fourth axis is in this direction. So there's z3 has been rotated clockwise. Okay, so it's a minus 90 about x3, and it has become z4. Well, now a3, what are the distances here? So the distance between the z-axis z3 and z4, there's an a3. Okay, so that is my link length a, and then there is d, which is the offset distance between the x3 and the x4. So that's my d4. So what will happen to this table? So it will be a3 here, d4, and theta 4 is the angle. Now if you look at subsequent frames, 4, 5, 6, the origins are there. That means there is no shift in the origin. This is a very, very important point to note, because when we come to inverse kinematics, this actually enables a solution to exist. Okay, so please note. So if the origins are the same, what happens? There is no change in A and D parameters. Why? Because the A and the D will become equal to 0 if the origins are same. So the offset distance and the link length will become 0 because the origins are at the same point, right? Now, so at 5 it becomes 90. So Z5 is that side. Now, where is Z5? It is rotation anti-clockwise about the x4 axis by 90 degrees. That's how Z4 becomes Z5, right? So there is a 90-degree shift here. So there is 90-degree shift here. Now it's anti-clockwise, so it's plus. Origins are same, so this 0, 0, this theta 5. Now again, Z5 is that side. It rotates clockwise, okay, about the, so it rotates like this. Now this is clockwise about the x4 axis, and Z5 becomes about Z5, and Z5 becomes Z6. Okay, so what happens here is, the last will become, because it's a rotation clockwise, so it is minus 90, 0, 0, theta 6. Okay, so this is our DH parameter table. As I was saying in my last class, please do this by yourself, assign the axis by yourself, write down the DH parameter table, and this should be clear, because most of the robots we'll be talking about would be 6 degrees of freedom. Okay, so to do forward kinematics, inverse kinematics, this should be clear. How did this table come, and how are we going to proceed from there? Okay, so next what do? We have to take each column of this. Okay, let me go forward. Now next what do? I need to find the matrix T0 to 6. And how do I find that? I multiply this. I multiply all the matrices T0 to 1 into T1 to 2, 2 to 3, T to 4, 4 to 5, and 5 to 6. I multiply all of this. So I need to find each of the individual matrices T0 to 1. This will be my T0 to 1, T1 to 2, T2 to 3, T3 to 4, T4 to 5, and T5 to 6. Okay. And how do I do that? I take one row at a time. So I take this, the joint number. So I take these 4 parameters, A, alpha, D, and theta, and put it into this generalized matrix. I get the first transformation matrix, which will relate frame 1 to frame 0. Okay. Then I take the second one, put it in there, then third, fourth, fifth, sixth, like that. So there'll be 6 of them. Okay. Now let's see further. So when I do that, the first transformation matrix is this one. Now please note that the origins are the same. So if you look at the matrix here, the origins are same, so that is 0, 0, 0. There's no shift of origin. There is a rotation of about z-axis by an angle theta 1. So this is my rotation matrix. So this is what the matrix is. Okay. The second matrix is given here. The second transformation matrix relating frame 2 and frame 1. Here also, if you note that the origins are the same. So this is 0, 0, 0. But it has been rotated. Z2 has gone in that direction. Okay. So that is accounted for here now. Okay. So the Z2 has been rotated, has an angle of 90 degrees with respect to Z1 and Z0. Okay. So this is transformation 2. Transformation 3 is here again. Now transformation 3, this is my Z2 and this is my Z3. And that's my Z3 axis. That means Z3 is a rotation about Z-axis again. So this is a rotation about Z-axis. This is the road by theta 3. And the origins are shifted by a distance of A2 in the X direction. Okay. So for the 0 frame, this is my X direction. So it is shifted by A2, which is coming here. And it is shifted by, in the Y direction, it is 0, and it is shifted in the Z direction by how much distance? It is shifted by D3. Okay, so where is D3? D3 is here. Okay, so X, Y, and Z directions, it is shifted, so it is A2, 0, and D3. Okay, the second to the third. Okay, now what about the fourth one? The fourth one also, there is a rotation. The fourth axis, the Z3 and the Z4 are orthogonal. So if you look at it, the structure will become like this. So it is similar to this, if you look at the structure there. And there is a shift of, the link length is A3 and this is D4. Okay, so that's the fourth rotation matrix, which is between the fourth frame, which is here, and the third frame, which is here now. Okay, so now we have got 4 of them. Let's look at, in the previous one, we got 4 matrices, right? 1, 2, 3, 4. We need 4 to 5 to 4, and 5 to 6. Exactly the same way, there's a shift in the Z direction. So there is no change here and here and here, because the origins are the same. Only there is a rotation about the Z-axis, and the Z-axis has been shifted by 90 degrees. Similarly here and similarly here. So these are the 6 rotation matrices that we have got. Now I want to find the total rotation matrix. So I want to find the total rotation matrix 0 to 6, which becomes equal to 0 to 1, T1 to 2, T2 to 3, then T3 to 4, 4 to 5, and T5 to 6. Okay, 1 to 2, 2, 3, 3, 4, 4, 5, 4. These are all multiplications. Okay, so that is we have just found the 6 matrices. Now we multiply them out to get. Now as you can see that in the previous case, when we talked about a 3 degree of freedom system, it was pretty simple. Okay. Now, well, it is still simple, but the expressions become very long, and there's a very high chance of making a mistake. So very often, to do forward kinematics, inverse kinematics, we use a computer program. Now please note that we'll do the multiplication in a particular sequence, and it will become clear as we go along why do we use that particular sequence. Okay, so instead of multiplying straight away, like what I mean is, in the case of 0 to 3, what I did, I simply multiplied 0 to 1, 1 to 2, 2 to 3. I multiplied in this order. Now I will multiply in the other order. So I'll multiply 4 to 6 first. So these two I will multiply first. Okay, so this is 4 to 6, that is 4, 5, 5, 6. These two transformation matrices, I get this. Okay, then I will multiply 3 to 4. So first multiplication is this one, then the second one is this one. Okay, I'm not changing the order of the matrices, so it doesn't matter. Okay. Then I'm going to multiply 3 to 4. So I get 3 to 6 as this matrix. Okay, so we are getting 3 to 6 matrix as this one. That means relationship between the 6th frame to the 3rd frame, which we have got by multiplying this much. Now these 3 matrices we multiplied. Then what I do, I multiply this one, 3rd. So what I do is I multiply these two. Okay, so what we do get is 1 to 3. I multiply these 2 matrices and I get this. Then I multiply 1 to 3 into 3 to 6. Okay, so what do I get? I get 1 to 6. Then I get 1 to 6. I multiply this. 1 to 3 I'm getting here, and 3 to 6 I got previously. So I multiply those 2 matrices, I get 1 to 6. Now the expressions become very long, as you can see. So we are just writing this down by 1 to 6 matrix is written this way, R1, 1, 1. Okay, so this is my first term, second term, third term. So the way it is written, R from matrix 1, 2, 1, 1 means row number 1, column number 1. R1, 2 means row number 1, column number 2. Okay, R1, 3 means Px means the distance in the del x. So the distance between the origins of the first frame to the 6th frame in the x direction. That's the meaning of Px. That's what I was trying to explain here. Okay, so if you look at the terms, this term is actually this one. So 1 R11 is equal to cos 2, 3, cos 4, cos 5, cos 6, minus sin 4, sin 6, bracket close, minus sin 2, 3, sin 5, sin 6. Okay, so if I open it and write, this will basically mean cos theta 2 plus theta 3. Okay, then we have cos theta 4, cos theta 5, cos theta 6. Okay, minus like that. Okay, I hope you understand. Then minus this term here. Okay, so what you can see is that the expressions are pretty long, and they appear in all kinds of combinations. Cos theta 2 plus theta 3 into this full bracket term, which has some more cos and sine terms. Okay, so this is we are doing it like this. It will become clear why when we go to inverse kinematics. Okay, basically you cannot solve the inverse kinematics unless you do it this way, and this has a particular property. Okay, now we have got T0, 1 to 6 only. Okay, now I want T0 to 6. So what will I do? I'll simply multiply this with 0 to 1. Okay, then it will become 0 to 6. So with this matrix, I multiply 0 to 1, the first transformation matrix, and I get my full matrix, which is going from T0 to T6. Now if you look at the expressions, R11, R12, R13, R11 is this one. So you can see that it has become a very, very long expression. Okay, so it is cos theta 1 bracket cos theta 2 plus cos theta 2 plus theta 3, again bracket cos 4, cos 5, cos 6 minus this. So you can see that the expressions become very, very long. Okay, now if you have a 10 degree of freedom system, you're trying to do 0 to 10. you can imagine how long the expression will start becoming. Okay, so this is basically to show that there are sine and cos terms and they appear in all kinds of combinations. So what does this give? This gives us the total rotation. Okay, and what is this? This is the distance between the origins. Okay, origins. Okay, which origins? 0 to 6. Distance in the del x. This is the distance in the del x, del y, and del z between the origins of the frame 6 and the frame 0. Okay, so this is in the x direction, the y direction, z direction. Okay, now this is how we do the inverse kinematics of a 6 degree of freedom system, and this is how we do the relationship between the end effector coordinate and the 0 frame of n degree of freedom system. In this case it is 6. In the previous case we had done for 3. We have also done for 4. Okay, now let's move on to the second part of our discussion, in which we will talk about the forward kinematics of a system. So we will talk about forward kinematics. What does this mean? So we will talk about forward kinematics. Now before we go there, let me try and explain that how does a robot actually work. So we have a manipulator like this. Okay, now at every joint there is a motor, there is an encoder or a position sensor at the back, and there is a gear in front. Okay, and this way of controlling a robot is basically called independent joint control. So independent joint control means that we are controlling every joint independently of the other joint. Okay, and each joint is actuated. So each joint is actuated by an actuator. So in this case it's a motor, electric motor. Most commonly actuator, there is a sensor, position sensor, which is an encoder, and there is a gear. Okay, set. So each of these joints will be having a gear. Here there is a motor and there is an encoder at the back. How is the motor actuated? The motor is actuated by giving it some voltage input. Okay, so when I give some voltage to the motor rotates. Okay, so my input is voltage and the voltage to motor. The motor rotates. So motor rotates, and this rotation will cause change in joint angle. Okay, so voltage V, motor rotates, change in joint angle theta, and when there is a change in this, my theta 1, this my theta 1, this my theta 2, this my theta 3. So when there is a change in my joint angle, what will happen? The end effector coordinate will change. Okay, so my end effector coordinate, this one here, if I say this is my x, y, and z, then that x, y, and z will change. We can also assign another frame here like this. Okay, that also I can do. So the coordinates of the end effector, in this case let's say frame 3, is going to change. Okay, so we have given a voltage, the motor has rotated, the motor rotation is causing a change in joint angle, and the change in joint angle is causing a change in the end effector coordinates. Okay, now please note that the spaces are different. What do I mean? So this is what we call the actuator space. So this is my actuator space. Okay, where we are giving a voltage and the voltage is driving the motor. Then we are having the joint space, which is my theta. Okay, and then when the joint space, there is a change in the theta, what happens? The end effector space changes. So end effector position changes, and that is my end effector space. So we have an actuator space, it goes like that. The joint space, something changes, the joint changes, it goes to the end effector, and end effector space, the position of the end effector changes. Okay, so it is forward and backward like that. Now here is my voltage in my actuator space. Joint speed is in degrees or radians, and here this is end effector space is in Cartesian coordinates. Okay, so please note that this is volts, then this is in degrees or radians, this is in Cartesian coordinates, which is x and y. So all the spaces are actually different and they're connected in some way. Okay, so basically what we are interested in is if I give some joint angle, if I change the joint angle, how is the end effector going to change? That is what is basically called the forward kinematics. So if I give input theta, then xy will change at the end effector. Okay, but the inverse of that is if I want a particular xy in the end effector or the last frame, then what is the corresponding joint angle that I need? That's the inverse problem. Okay, so let's look at define it this way. I draw my 3 degree of freedom manipulator again. So this is a 3 degree of freedom manipulator. Okay, now let us assign our axis. I'm going to assign my axis Z0, Z1, Z2, Z3. My X0 is here, X1, X2, and X3 is here. Okay, then what do we do? This is my theta 1 angle. This is my theta 1 angle. Okay, so theta 1 angle is the angle between X1 and X0. This is my theta 2 angle, that one, and theta 3 is this one. Okay, that is the three angles. Now how did we proceed? We assigned the z-axis, we assigned the x-axis, then we make DH table, then we make transformation matrices. Okay, I minus 1 to I, then we find the final 0 to n transformation matrix. That's what we were doing. So if you look at this, and I make the transformation matrices which I made I think in the last class, please refer back to that note. I made my transformation matrices T0 to 3, which was equal to T0 to 1, T0 to 1 into T1 to 2 into T2 to 3. And the matrix came out to be of the form cos 1, 2, 3 minus sine 1, 2, 3. And this is 0, 0, 1. This is sine 1, 2, 3, cos 1, 2, 3, 0, 0, 1. This is L1 cos 1 plus L2 cos 1, 2. L1 sine 1 plus L2 sine 1, 2. That is 0, that is 0, 0, 0, that is 1. Okay. Now, this is my final T0 to 3. This is my link length L1, L2. Okay. Now, this part is the rotation part. So here, this is my rotation. That is my translation. Okay. Now, what is the meaning of this matrix? This is a homogeneous transformation matrix, and it's very important for us to understand. Now, this is basically giving me the distance del x, del y, and del z between the origins of the third frame and the 0 frame. That is the amount of distance it has moved. Okay. So if this is the coordinate of this point, x, y, and z, this is planar 2D. Okay. So there is only x and y, there is no z, because this cannot come out of plane. Okay. This has to move on the plane. It's a planar manipulator. So it is 2D, so there is only x and y. Okay. Now, what is the value of this x here in the end effector? So x will be equal to this one, y is equal to that, z is equal to that, which is 0. So x is equal to L1 cos 1 plus L2 cos 1, 2. What is y equal to? Y is equal to L1 sin 1 plus L2 sin 1, 2. Okay, so we have got two equations. Okay, now what about the total angle? So my total angle is this one. So if I say cos phi, if phi is the total angle, then cos phi is equal to cos 1, 2, 3. Okay, and sin phi, similarly sin phi is equal to sin 1, 2, 3. Okay, so that's where it's coming from. Okay. So the total angle, if I say my total angle here, so if this is my total angle, if that is the total angle phi, then phi is equal to is equal to theta 1 plus theta 2 plus theta 3. Okay, because this is a planar manipulator. Okay, so we have how many unknowns here and how many knowns. So in terms of x and y, you have theta 1, theta 2 and theta 3 are three unknowns, and you have three equations. The first equation is here, second equation is here, and the third equation is there. So you can combine these two and get that. Okay, so we have three unknowns and you have three equations, so you can solve and get the values. What I mean, if I give you L1 and L2 are the link lengths, so they're fixed. If I give you theta 1, theta 2 and theta 3, you can tell me what is x, y and phi. So here if I give you theta 1, theta 2 and theta 3, you can tell me what is x, y and phi. And this is basically called my forward kinematics problem. Okay, so in forward kinematics, I give you the joint angles and you tell me what is the position orientation of the end effector. Now inverse of that problem is the inverse kinematics problem, which is more useful actually. So in the inverse kinematics problem, what do we need? We need basically the position orientation, the joint angles which correspond to a particular position orientation. Suppose I want to go and pick up an object now. So this is my object, this is my manipulator. Okay, I want to go and catch this object. I want to go to this point P1, which has coordinates x, y, and there is some orientation phi. Okay, this is kept on a table, let's say. So I want to go to this point and catch it like that. Okay, this is what I want to do. Okay, now to be able to do that, I'm going to give you x, y, and phi. Now you tell me what is theta 1, theta 2, and theta 3. This is called the inverse kinematics problem, the inverse of that. This is of course more useful because when a robot has to move in space, we are interested in the position orientation of the end effector. Okay, now let's define it this way. So this is my forward kinematics. This is called forward kinematics. So what am I going to give? I'm going to give the link angles. Okay, so in this case I'm going to give thetas. What is the output? The position orientation plus orientation of end effector. Okay, so position orientation means x, y and phi of the end effector. Now so this is called the forward kinematics problem. Now if I do the reverse of this, so if I do the reverse of that, the reverse of this is, suppose I give this as input. This is my inverse kinematics now. Okay, so if I take this and put it here, I will get my thetas. So if I give input x, y and phi, you should be able to tell me what is the thetas, right? That is the inverse kinematics problem. I hope you understand the meaning of forward kinematics, inverse kinematics. We will talk about the concept of solvability, that when can you solve and when can you not solve. Okay, so the question of solvability is there. When can you solve this problem and when can you not solve this problem? Okay, now here how many variables are there? There are three variables. And how many equations are there? Three equations are there. So it is solvable. But what I would like you to note is that if your equations are like this, okay, in the case of the Puma robot, the x, y, z and alpha, beta, gamma of the end effector, there is 6, is a function of 6 variables, 6 thetas. Okay, but these thetas appear in all kind of combinations like this. Okay, so it is not guaranteed that you'll be able to solve all the time. Okay, so please note this, that I hope you can understand and you can appreciate this, that these equations are having sine and cos in all kind of combinations. Okay, and this is what makes it very difficult to solve, and you may not be able to solve. Okay, there are manipulators where solutions don't exist, closed form solutions don't exist. Okay, so that is first thing we need to know, is that when we are saying how many equations are there and how many unknowns are there, just because the number of equations and number of unknowns are equal does not mean that you can solve. Okay, that's the first point. The second is we need to understand that this xy is a function of theta 1 and theta 2. Okay, and if I want theta 2 or theta 1 and theta 2, then basically I need to take the inverse of that, of xy here now. So this is my forward kinematics and that's my inverse kinematics. Okay, now let's look at an example, the same example. Let us look here. So we have this 3 degree of freedom manipulator. Now let me draw the 3 degree of freedom manipulator again. Okay, now how do we proceed to do the forward kinematics? First you write your assign the axis z0, z1, z2, z3. I've done this a lot of times. Then x0, x1, x2 and x3. Then these are the link lengths L1, L2 is given, right? Now we just derived the equations. Just the last slide we had derived x is equal to L1 cos 1 plus L2 cos 1 2. Y is equal to L1 sin 1 plus L2 sin 1 2. Okay, and phi, the total angle is equal to theta 1 plus theta 2 plus theta 3. Okay, so 3 unknowns. So x, y and phi are a function of theta 1, theta 2 and theta 3, and there are 3 equations, 3 unknowns here now. Now in the forward kinematics problem, forward kinematics, suppose I give you given numerical values. So theta 1 is equal to theta 2 is equal to theta 3 is equal to 30 degrees, just for example. Okay, now the link lengths are also equal. L1 is equal to L2 is equal to 1 unit. Okay, now I want you to find what is the position orientation of the end effector. Okay, so this is question number 1. What you're supposed to find position and orientation of end effector. Okay, so we are given you all the joint variables. Now you find what is the position orientation of the end effector. In this case is the frame 3. How do we do that? Well, it's very simple. Take these equations, equation 1, equation 2 and equation 3. So put the values in equation 1 and equation 2. So x is going to become equal to L1 is equal to 1. So it is cos 30 plus cos 60. So 30 plus 30 is 60. So that is cos 30 plus 30. Okay. So which is equal to cos 30 plus cos 60, which is equal to, you can very easily calculate that, 1.36. L is given as 1. Okay. What is y? Y is equal to sin 30 plus sin 30 plus 30, which is equal to sin 30 plus sin 60, which is again equal to 1.36. Okay. So what is the coordinate of this point? XY. So the coordinate of this point is 1.36, 1.36. Okay, that we have got from forward kinematics. Okay. With respect to which frame? With respect to the 0 frame. This is my Z0, this is my Y0. Okay, this is my X0. Okay. So with respect to the base frame, this we are getting with respect to base frame now, 0 frame. Okay. What is phi now? Phi is equal to theta 1 30 plus 30 plus 30, which is equal to 90 degrees. Okay, so it will look something like this. This is 90 degrees, so it should be here, there. Okay, so now we are seeing that this is my forward kinematics. I have given the values of thetas, I have put in the values of thetas, and I'm getting the values of the position orientation of the third frame. Please note this is position orientation of frame. Although we are saying find position orientation of end effector, here it means frame 3. Okay, now suppose I want this point. Let me put it here now. So let me put another, I want this point now. Okay, let me call this x dashed y dashed. Then I need to put another frame there and say this is my frame z4, this is my x4. Okay, now x3 and x4 are in the same direction, so your phi will still remain the same, only this fellow will shift. So what will happen is this L3 will get added on there, and what will happen is you'll get one more term here, so it will become L3 cos 1 2 3, okay, plus this will become L2 sin 1 2 3. I hope you understand. And Okay, so that is what will give you the coordinate of that point. Okay, so now in this particular case, we have found the position orientation of frame 3 with respect to frame 0. That's what we have done here. So you can actually find the last frame or the tool tip also, this tip also, by assigning one more frame. That's not a problem. Exactly one more term will get added on there. Okay, now so this is basically what we call the forward kinematics, and this is giving me the position orientation of the third frame with respect to the 0 frame. So third frame with respect to 0 frame. Now if you want to find the case for the Puma robot, well, we can do for the Puma robot also. Say, let's go back and very quickly look at it. The Puma robot has 6 degrees of freedom. So basically we have to give the 6 variables, you give the 6 thetas and all the joint parameters like A and D which are there, and then proceed. Okay, now as you can note that this is going to become it's not very difficult, but there are so many terms. Okay, so it will be difficult to do by hand. If you do by hand, then there is a chance of a mistake. Okay, that is the only downside of this. Okay, now let us look at the Puma robot very quickly. So the Puma robot, this is what we got. So this is my, so in the case of the Puma robot, let's just go back and look at that once. Okay, let me just come to the figure. Yeah, so we have got the figure. So here we have 6 thetas. What I'm trying to say is, suppose I want the position and orientation of the last frame. I want my x, y, z, plus I want alpha, beta, gamma. Okay, so there are 6 because this is a 6-tier system. So there are 6 thetas. Okay, and there are these joint variables, which is A2 is there. A2 is one joint variable here. Then there is a D3. Then what else is there? D3 is there, and on the front side what we noticed is we have D4 and we have A3 and D4, right? So we have A3 and D4. So we have A3 and D4. Okay, these have numerical values, these are link lengths and offsets, so they are fixed. So this is fixed. Now suppose I give you the 6 thetas and I say you find out the position orientation of the end effector, find out the x, y, z and alpha, beta, gamma. Okay, I'll give you the 6 thetas. So what you can do is, what we need to do is we need to write this equation, the final equation that comes out in this form. Okay, so this is my x, that is my y, and this is my z. So simply take the values. Just for example, if I say theta 1 is equal to theta 2 is equal to theta 3, theta 4, theta 5, theta 6, they are all equal to 10 degrees, just for example. Then you take all this, so this is cos 10, okay, plus A2, I give the values A2, D3, A4 is equal to 1 unit. Okay, so I just give these values, that the values of A2, D3, A3 and D4. A3 and D4, A3 and D4, these are all equal to 1. Then you put in the values of cos, sine, A2, D, A and D parameters, and you'll get your x, y and z. Similarly, after you get your x, y, z, you have to figure out what is the total orientation. Okay, so we can use the orientation. So this will give you the total orientation. Each one of this is going to give you the total orientation matrix is this one. That will give the orientation of the end effector. Okay, so this is my orientation, this is the position. Okay, so this is how we do the forward kinematics of a robotic system. So today we looked at the forward kinematics of the robotic system. I took a we looked at the Puma robot. So we completed the Puma robot as we started in the last class. Then I looked at the forward kinematics of a 3 degree of freedom planar manipulator system, and we saw that there are 3 equations and there are 3 unknowns, so we can solve. However, keep in mind that your thetas come in all combinations, okay, multiplications and additions, so theta 1 plus theta 2 in that order. So it is not always guaranteed that you can solve. Okay, there are manipulators which do not have solutions. For example, the human arm does not have a closed form solution. Okay, So today we finished off with talked about the forward kinematics. In the next class, we'll move on to the inverse kinematics and see that how do we proceed with the inverse kinematics. So we'll stop here today. So thank you.